Hello, welcome back. Let's look at another problem involving a rigid body. Force P of magnitude 90 is applied to member ACGE that is supported by a frictionless pin at D and by the cable ABE. Because the cable passes over a small pulley at B, the tension may be assumed to be the same in portions AB and BE. All right. It's a little bit helpful that it mentions that, but even if it didn't, when pulley B is frictionless, tension in this cable is always the same. Wherever you cut it, you get the same tension. For the case when A equals 3 inches, determine the tension in the cable, okay, and the reaction at D. All right, so this is a rigid body. Because there are multiple supports, there's a cable applied at different locations. Force P is at a different location. We cannot ignore the size. The forces don't go through the single point. So this will be a rigid body equilibrium problem. Step 1 is always to draw a free body diagram of the rigid body. In this case, we only draw the free body diagram of ACDE. And step 2 is to apply equations of equilibrium. In a 2D problem, we have 3 equations. Summation of forces in X got to be 0. Summation of forces in Y has to be 0. And summation of moment about any point you want to pick also should be 0. Hopefully, we have only 3 unknowns in problems such as this one, because we only have 3 equations that we can apply and we can solve 3 unknowns for. So let's just start with that step 1, which is drawing the free body diagram of this member. So free body diagram of ACDE. Step 1 in drawing free body diagram is always isolate. In this case, isolate ACDE and then draw outline of ACDE. Isolate means remove the cables. The cable ABE, remove pin D, remove supports, anything else, just isolate and then draw the outline of this member or rod or beam. You can certainly label it, the points on it, so it adds a little bit more clarity, but you don't have to. All right, step 1 is done. Step 2 is put all the active forces and moment on the free body diagram. When I look at this, the only active force that I see is this force of 90 pounds being applied at point C. I don't see any other moments, any other forces. And step 3 in free body diagram is to put reactive forces. These are the forces that are trying to mess up the equilibrium. That tension in the cable, again, it could, some people take that as a reaction force because it's pinned to point E and A and is pulling on it. But it could also be an active force, meaning it's trying to maintain the equilibrium. It really doesn't matter which way you, which step you added to the free body diagram, you have to add it anyway. In this problem, I chose to add it in this step as a reactive force. Which is not incorrect. So I have a tension. Tension, remember, means you put it, the going away from the point. So that's the tension. It kind of follows, and at point A, it is going at an angle. Do I know how much? Yes, this is 5, this is 12. So I'm looking at a 5, 12, and 13 slope triangle. One more thing that I have is a pin at point D. If you've watched other videos, you know that I always make a table. I either write moment or rotation, and then I see which way this pin is not moving and which way it is moving. So when I look at the pin, and only we look at the pin itself, we don't look at anywhere else on the diagram, we only look at the pin. In this case, it is not moving in the x direction. It is not moving, sorry, this should have been y, not moving in y direction. Can it rotate about point D? Yes, that's the whole purpose of having a pin. And wherever you see a no show up, that's the direction you need to add a force. So I'm going to add a force in x direction. These are both unknown, so both of them I drew in the positive direction. We can add the length a little bit if you want to. This whole thing is 12 inches. This portion of it is 3 inches. This length here is given to be 7 inches. So step 1, which was drawing the free body diagram, is done. Now we got to move on to the equations of equilibrium and solve for the 3 unknowns that we have. We have t, and we have dx and dy. So 3 unknowns that we have to solve for. So redrew the free body diagram right here, so we have it available. Equations of equilibrium. If I take moment about point D, I don't have to worry about dy and dx because they pass through that point. I should be able to find my tension by just writing that one equation. Summation of moment about D is 0. Rotation counterclockwise, I take it as positive. I usually start from one side and kind of move and make my way through the beam or through my rigid body so I don't miss any forces. I start with that T. That T is going to have 2 components. This one is T12 over 13. This one is T5 over 13. Each of them is going to have a moment about point D. So let's see. T5 over 13, the horizontal one. The distance between the horizontal one and point D is right here, and that's 12 minus 3, so that's 9 inches. 9 inches. All right. Which way is trying to move? It's trying to go this way, and that should be a negative because it goes against my sign. Next, I have T12 over 13. That one, the distance between line of action of this force and D is given to be 7 inches. Trying to rotate about point D in this direction, which is also negative, so I put negative here. Kind of making your way through, I reach to the 90 pounds next. The distance between line of action of this one and point D is that 9 inches again. Trying to rotate this whole thing about D counterclockwise, so that's plus. Making my way through dy and dx, I don't have to include them. They pass through point D. The moment about point D of both of those forces are 0. The distance between each of them and point D is 0. Next, I have the other T up there at point E. The distance between point D and this line of action of this force is 3 inches. That is trying to rotate counterclockwise, which is positive. All right. So let's see. I only have T in this equation. So once you rearrange it and solve for T, you should get T equal 117 pounds. And that's the tension in the cable. All right. So I used one of my equations and I found one of my unknowns. I have 2 more equations and 2 unknowns, so I should be able to do it. You can pick and choose which one you want to do first. Next. Should not matter at all. Summation of forces in x equals 0. Anything points to the right is going to be plus. Same method. Starts from one side and kind of make your way through. I have the T horizontal, the T, which is 117 pounds, 5 over 13. That's the horizontal component, and that is negative because it goes against my sign. Vertical T, I don't need to worry about it. Keep moving. I reach to the plus 90 pounds. Keep going up the beam. I get plus dx. And I get minus T, which is minus 117 pounds equals 0. All right. One unknown here, only dx. And if you solve, you will get dx of 72 pounds. Use two equations, two unknowns. Now I'm going to use my last equation that I know, and hopefully I can find the last unknown. Again, starting from the left, making my way through. I'm going to go a little bit faster here. You can pause and look at it and figure it out if you have to. This one is plus, and then plus dy equals 0. Only one unknown. dy is minus 108 pounds. You might wonder why it's negative. Means the way I drew my free body diagram, the dy in reality is opposite of what I drew it there. So dy in reality should have been like this. So dx is 72 and dy should have been down here. You do not have to go back and correct the free body diagram. You don't have to do anything. You don't have to explain it. This is totally correct and this is your final answer. Just know that this negative means it is opposite of whatever you drew on there. There's a little sneaky point in this problem. It says reaction, the reaction at D. And I found dx and dy. One more step you have to complete to fully get this credit for this problem is to find reaction at D. It means magnitude and angle of one force. So let me redraw it here quick. I have dx of 72 pounds, dy of 108 pounds. Should have put this outside. Pounds. So this is my resultant D. So magnitude, so my D is 72I minus 108J units of pounds. Magnitude is going to be 72 pounds squared plus 108 pounds squared. If you do the math on this one, you get 129.8 pounds. Can I find this angle theta? Yes, sure I can. Tangent theta equals this, which is 108 over 72. Pounds, they get canceled each other out, and theta is going to be 56.3. So if you find dx and dy, that's totally fine. But again, this problem, since it says the reaction at D, it's better to just present it as one force and one angle. Thank you very much.